This is the group project for CS 559 Machine Learning Fundamentals and Application. The topic is house price prediction, and the group members are Harsh, Jayraj, Nidhi, and Sophia. This is group number 1. We have conducted this project in 6 different parts. The first, discussing and studying the dataset. We try to find patterns in raw data and try to make sense of the features that could be used or need to be dropped. Then we discuss the problem statement, the why of the project. Why exactly we are working on this project? What do we gain from it? Then we move on to the EDA section where we try to engineer the features and create patterns which could potentially be useful. Lastly, we work on a heat map to build correlations, only after which we get to training our models. Finally, we draw conclusions from the project at hand. Looking at the dataset, it comprises of 79 explanatory variables that cover practically every little detail a house can have, from trivial things like number of rooms to minute features like garages. The data is of 1460 houses and 79 columns related to each row. The target value for each row is the price and is located in a different Excel file which needs to be combined before working. Now the problem statement. The idea stems from the ideal price for a house, or predicting a good price for the house before it is listed, making it convenient for both parties involved. Number of bedrooms, floors are the obvious factors, but even niche factors like location are taken into consideration. Finally, the goal. The goal of our project is to train machine learning models which could be beneficial in prediction and house price analysis.
So here is the EDA part of our project. Firstly, we have dropped all the columns which have null values in the dataset. Then obtained the correlation matrix to check the correlation of independent variable with respect to its dependent variable. Then eliminated all the least important columns from the dataset. After this, we have plot the visualization, that is scatter plot for the sale price, which is our target variable. So from here we can understand that all the points are assembled on the bottom and there seems to be no large outliers in the sale price. Next, we have plot our heat map. So this is just a snippet of the heat map. The complete one can be found in the notebook. So from this we can observe that there is no direct pattern observed here. Secondly, continuous numeric value seems to be affected the correlation between two variables. Also, the column overall quality is directly correlated to the target, that is our sales price, which value is around 0.795437. So, from this graph, it can be observed that the sale price of the house increases exponentially with respect to the overall quality of the house, which seems to be pretty obvious, I guess. Same insights can be obtained from this graph, where the total number of rooms above ground, where similarly the sales price have been increased with respect to the total number of rooms above the ground.
After completing the EDA analysis, we started to train the models. The 5 models we used were linear regression, random forest, Gaussian process, XGBoost, and a stacking model. The linear regression model achieved an RMSE of 939. The random forest regressor used 500 estimators and achieved an RMSE of 403. The Gaussian process regressor used kernels and achieved an RMSE of 1054. The XGBoost regressor used 10 estimators with a max depth of 5 and achieved an RMSE of 1984. And the stacking model, which incorporated the 4 previous models with linear regression as the final estimator, achieved an RMSE of 823. We tried stacking with each of the 4 models as the final estimator, and the linear regression model yielded the lowest RMSE. Overall, the random forest and stacking models achieved the lowest RMSEs. Random forest's RMSE was the lowest at 403, and the stacking model was the second lowest at 823.
So as we reach to the end of the project, let me briefly restate these main points. We are a 4-person team that initially evaluated the dataset and split our work. We used linear regression, Gaussian process, random forest, XGBoost, and ensemble model through the stacking approach to develop this model. in which the data was trained using random forest regressor, which resulted in the lowest RMSE. The next to lowest RMSE was attained by the stacking model, which used linear regression as its final classifier. The root mean squared error or RMSE generated for the models is as follows: 939.68 for linear regression, 1054.74 for Gaussian process, 403.81 for random forest, 1984.86 for XGBoost, and 823.78 for stacking.
So, in conclusion, we can say that the best performing ideal model was the random forest model as it achieved the lowest RMSE. The stacking model was outperformed by a narrow margin and had a linear regression model as its final classifier. This has been our project. Thank you for listening.